Liz Cottrell. I'm in the Department of Mineral Sciences, and I direct the Global Volcanism Program. I'd like to welcome our interns here today. We're thrilled to have you here this summer. Welcome, welcome. Okay, so I like to say that I study the other 99.999% of the planet. Underneath all the scum at the surface, we have the deep earth. We've got a rocky mantle, that's the orange up there, that's silicate solid rock, surrounding a nougat center of liquid iron alloy. Okay, this is important. The deep earth is the source of our hydrosphere, all the atmosphere, all the ocean, outgassing of the deep earth. Okay, and it determines the habitability of a planet. So if you're interested in exoplanets or whether a planet in another solar system that we observe remotely might have life, you need to understand whether the materials on the inside of the earth can hold life-giving constituents like water and carbon. To study the deep earth under the extreme pressures and temperatures requires extreme samples and tools, and that's what I'm going to give you a little window into today. So my group addresses questions such as, how did our planet differentiate into a mantle and core in the first place? And what's the composition of the core? What are the concentrations and distributions of oxygen, carbon, and water? And how do those important constituents cycle between reservoirs in the deep earth and also between the surface and the Earth's deep interior? And today we're going to talk about just about carbon and water. So, big question. What is the next net flux of carbon between the surface and the deep interior? Everyone knows carbon's important. It's a greenhouse gas. Planet is warming because of increased carbon dioxide in the atmosphere. What you might not know is that an estimated 90% of carbon on Earth is actually in the deep earth, not on the surface. And so this has incredible leverage. It's the elephant in the room of carbon. Volcanoes bring carbon from the interior of the Earth to the outside. So volcanoes underwater, mid-ocean ridge volcanoes, illegal laser pointer usage here. Volcanoes outgas CO2 under the water, and at volcanoes on land at subduction zones, the so-called ring of fire. The plate tectonic cycle also takes carbon from the atmosphere and the oceans and stuffs it back down into the deep earth through subduction. Okay, so we have carbon out and carbon in. The state of the science is such that we don't even know if the net flux is positive or negative, if the deep earth is contributing carbon to the surface or removing it, helping us. And so I'm trying to get at this question by looking at the net outgassing. I have a postdoc, Marion Lavoyer, funded by the Deep Carbon Observatory of the Sloan Foundation, to use Smithsonian's outstanding seafloor glass collection. These are about 13,000 volcanic glasses from underwater submarine volcanoes, shown here in yellow and white dots. And she is measuring the carbon content. Because these erupt underwater, the pressure of that water holds the carbon in. She's measuring the carbon content of these glasses directly because pressure holds the carbon in the glasses. Okay? We're not so lucky with volcanoes on land. They erupt directly to the atmosphere. The carbon is lost to the atmosphere. And so how can we monitor the thousands of volcanoes around the planet outgassing to space, out to the atmosphere? Well, we are engaging in a very high-risk project. We're attempting to measure for the very first time carbon dioxide emissions from volcanoes using satellite-based remote sensing. We have a postdoc arriving in September, funded by the consortia and the Deep Carbon Observatory, to do exactly this. And so we're going to try to quantify the flux of carbon from the inside of the Earth to the outside. Okay, but what about water? Now, the orange part of that section, that's a wedge of the cross-section I showed in the first slide. The orange part there is the mineral perovskite. It's the most abundant mineral on the planet. And we don't know whether or not it can hold water. How much water can it hold? And how does it affect the properties of the planet? So the pressures in this part of the planet are extreme. 6 orders of magnitude greater pressure than you're under right now. Gigapascals of pressure. We can use a little device that fits in the palm of my hand. It's called a diamond anvil cell. And we can load the mineral perovskite, about 30 microns across, that's the width of a human hair, onto, instead of the head of a pin, the culet of a diamond, and use those diamonds to push the specimen together to generate the gigapascals of pressure that are on the inside the deep earth. We have gigapascals of pressure then. We need to take this device then to a synchrotron radiation source. At these accelerators around the country, electrons are accelerated to relativistic speeds. They generate X-rays, which we can use to look at the specimen and interrogate the specimen. And of course, we need to go to very high temperatures, so we heat it with very powerful lasers. And when you have gigapascals of pressure, synchrotron radiation, and lasers, you are doing something, to use the new Smithsonian monkey ear, seriously awesome. And in fact, I took this photo yesterday. I was at the synchrotron, Brookhaven National Lab, all this week until this morning. This is Brent Gaholski, who's a Buck Fellow here, and the big smile on his face is because we think he is showing you here that little spike on the spectrum that he's pointing to on the screen, potentially the first measurement of structurally bound water in the mineral perovskite. Thank you. Okay, so I think the question is that one of my colleagues, who I guess is going to remain nameless, has stated that there's been a suggestion that volcanoes could be the cause, large volcanic eruptions could be the cause of extreme periods of warmth in the Earth's past. And could I comment on the potential of volcanoes to cause extreme warming? For millions of years. Okay, there are a couple really important points to make right now. I'm going to take the opportunity right now to tangentially answer that question. Number one, okay, for anyone in the room wondering if volcanoes could be responsible for present-day warming, absolutely not. Humans are completely responsible. The factor by which human-created anthropogenic CO2 is 150 times more CO2 than volcanoes emit to the atmosphere right now. So since before the start of the Industrial Revolution, in fact, humans have dominated CO2 to the atmosphere. Okay, so volcanoes are not causing warming today. And also really important to understand is that the effect of a volcanic eruption is not to warm the planet, even though half of the gas emitted might be CO2. The effect of a volcanic eruption is to cool the planet. And in fact, volcanoes often cause catastrophic cooling. Release of sulfur aerosols to the stratosphere block the sun's light reaching the surface of the planet, such that in the past, the eruption of, well, there have been many, Krakatoa, many, have caused catastrophic cooling and widespread famine throughout North America and Europe due to cooling, due to volcanic eruptions. So there's a bit of a complicated relationship between volcanoes releasing CO2, which causes warming, and sulfur, which causes cooling, which can last many decades, in fact, or years, depending on the size of the eruption. I wasn't quite sure what you meant by your question. Is there enough carbon to cause that warming, maybe in a single eruption? Is that what you're saying? It would really depend, I guess my answer is it would really depend on the composition of that eruption, because if it was sulfur dominated, the effect would definitely be cooling, at least in the short term.